Right. Morning, everyone. Just a small administrative announcement. Apparently, Zoom is changing its app this weekend. So maybe you'll have to reinstall it and it may require passwords. So I hope all of you remember the password, which is 17294104, the first two Ramanujan numbers. Okay, then. Share screen. Share screen. Share. Yeah. Okay. Super. All of you can see the screen? So today's co-host is Stefan. So he's the one letting people in and also monitoring the chat. I'm going to stick this in active speaker video. This means I can only see myself. Maybe I should show a few more faces. All right. I need to see a few faces looking at me pretending that they're following. Okay. So I decided I will do Kleene algebras on Thursday after the pumping lemma because I didn't want to interrupt today's topic, which is absolutely one of my favorites, and I didn't want to shortchange it. This is on the minimization of deterministic finite automata. I have put a number of notes on the course website. I hope people check the course website from time to time, like daily. So I put a number of new notes there yesterday evening. One of them is the details of how you go from NFAs to DFAs. I kind of sketched out how things work, but I didn't write down things in detail. So I wrote it. Those notes are from Comp 330 days. So everything is spelled out in detail. Probably most of you don't need to read it, but it's there if you feel like I'm going through fast. And this will be my general policy. In the actual live lecture, I may not tell you every single detail because it's kind of tedious to watch me prove basic lemmas by induction. Hang on a second. Hello? Yes. Hi, Ron. I'm in the middle of teaching a class on Zoom. Okay, you can send me email. Bye. My stockbroker probably telling me I'm bankrupt. Anyway, so I've forgotten what I was saying. What was I saying? Notes, yes. I put notes on NFA to DFA conversion. I put notes on minimization of DFAs, which is what I'm going to lead off with today. So again, I'll be a bit sketchy as I write and not fill out all details, but actually fairly detailed notes are on the website. So both these two notes that I've just described are in my handwriting and scanned. I got one comment from a student in Comp 302 saying my handwriting was unreadable. I hope you're not finding it so. And then I have notes, posted notes on the Myhill-Nerode theorem, which is going to be the second major topic. And I posted a link to a paper that was written by 6 people on duality for automata and another approach to minimization. So that will be the second half today. Okay, ready? We can launch. Let me just do a participant check. Participants, how many participants? I can't see participants anymore. 28. 29. Back to 28. I'm wondering if people are dropping the class. Right. So let me draw a finite state machine for you. This is exactly the machine that's on the web page. So it looks like this. So that's the start state. On 0, it just goes to itself. So the alphabet is 0, 1. On 1, it goes to a new state called S1. On 0, S1 goes to a state called S2. And on 1, it goes to another state called S3. And S3, like S0, is an accepting state. And S3 goes back on a 1. And it goes there on a 0. Okay, and then on 0, S2 goes to S4. That's on 0. S4 goes back to S2 on 0. On 1, S2 goes to a new state S5. S5 loops on a 1. On a 0, S5 goes to S4. Have I done everything? No. From S4 on a 1, we go to S3. Okay, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1. Okay, so here's our machine. What does it do? Any ideas?
It reads the multiples of 3.
Exactly. Well done, Maria. It tells you which numbers are divisible by 3. But how does it do that? Well, it keeps track of the remainder mod 6 instead of mod 3. So this corresponds to exactly the 6 possible remainders mod 6. And then it says, oh, if you're 0 mod 6 or 3 mod 6, then you're divisible by 3. But we know this is dumb because we know that there's a 3-state machine which does the same job, right? There's a 3-state machine which does the same job. You don't need to keep track of remainders mod 6. You just have to keep track of remainders mod 3. So this machine does what we asked it to do. It tells us it accepts binary strings exactly when they are divisible by 3, but it has redundant states. And so what we would like to do is, so this thing keeps track of remainders mod 6. Not necessary. So it has too many states. So if you were wondering, is there a unique DFA for a particular job? Oh my God, Siri, shut up. Okay, so it has too many states. So we would like to come up with some way of minimizing the number of states. So for those of you who were wondering, is there a unique machine for any given regular language? It's obviously not true. In fact, there are infinitely many machines for any given language. Most of them are badly designed. Okay, so we would like to find the best one. And since the only resource we're concerned about in finite automata is number of states, because that's the memory, and that's all that the memory you're allowed. There's no auxiliary, stacks and things that you can look up. So when we're thinking about optimizing a DFA, meaning minimize the number of states. So that's today's topic, how to minimize a deterministic finite automaton. Now, if you look at this machine, you will notice a couple of interesting facts. So look at delta S0, 0. This takes you to S0. And that's also what happens with S3. And if you look at delta S0, 1, Then this goes to S1, which is also what happens to S3. So this means once you get to S3, no matter what the next thing you read is, it doesn't matter whether you were in S3 or in S1, it looks exactly the same. So then you start wondering, why did I have both S3 and S1? You see that they're both accept states. So in every way, they're behaving exactly the same. And it's kind of obvious from this. So first obvious fact is, once you get to a state, it doesn't matter how you got there. What happens next only depends on what you read thereafter. Or not just next, what happens in the future only depends on what you read in the future. It doesn't matter if you got there by a simple path or a complicated path. Only the present state matters for predicting what's the future. In fact, this is the fundamental meaning of the word state, both in computer science and system theory and in physics. The state is what encodes enough information to predict the future. So you see S0 and S3, they're predicting exactly the same thing for the future. Why on earth are we keeping two distinct states? Okay, so as far as language recognition is concerned, S3 and S0 are exactly the same. So in some sense, there's an equivalence relation here. And the key insight is, oh, we're going to build a smaller machine by looking for an equivalence relation that captures identity of behavior, and then we will combine equivalent states. In short, we will build a new machine based on the equivalence classes of this relation. So that's the idea. So let's do it. So first I'm going to define the equivalence relation. I'm going to basically skip all proofs because they're all in my written handout. And anyway, they're dead easy. So here's the key definition. Given a DFA M, which consists of a set of states, a start state, a transition function, and an F with alphabet sigma, we say P and Q are equivalent. And we will write P equivalent to Q with its double wiggly line if for all X in sigma star, delta star Px is in F, if and only if delta star Qx is in F. So what's the intuition behind this definition? It says, pretend P is the start state. And then you're asking, if P is the start state, what's the language accepted? And what this equivalence relation is saying, if you take P to be the start state and ask what's the language, it's exactly the same as taking Q to be the start state and asking what's the language. So if you start from P and you follow any word, it will reach an accept state exactly when Q also does that. Okay, so is this equivalence relation clear? So it's good to contrapose this. When are P and Q not equivalent? So P not equivalent to Q means, you see there was a universal quantifier in the definition of the equivalence. So obviously there'll be an existential quantifier in the definition of not equivalent. So there exists an X in sigma star such that delta star Px is in F and delta star Qx is not in F, or delta star Px is not in F, and delta star Qx is in F. In short, P and Q disagree on what to do with X. One will say accept, the other one will say reject. Well, if they're saying different things for even one string, then they can't be equivalent. Okay, so that's just contraposing, or rather negating the definition of equivalence and pushing the negation sign inside the definition. Okay, so another observation. So when we write observation, we mean this is a thing that's so simple to prove that we're not going to bother to do the proof. So this is indeed an equivalence relation. So REL with a little n on top means relation. Okay, now some lemmas. So supposing P is equivalent to Q, then for all A in sigma, if you look at the next state, that'll also be equivalent to the next state if you go from Q. Okay, so this proof is obvious. So again, we will write, well, not obvious, you have to do something, but it's not a challenge for all the smart people whom I've let into this class. So right, so remember P means in square brackets is defined to be the set of Q such that P is equivalent to Q. Yeah, and so P is equivalent to Q can be stated as their equivalence classes are the same. You notice this is equality. I'm just telling you things you already know about equivalence classes. All right. So what this lemma just said was that delta plays well with the equivalence classes. In short, if the equivalence class of P is the same as the equivalence class of Q, then the equivalence class of delta PA is the same as the equivalence class of delta QA. Which means I can define a transition relation on the equivalence classes, and I'm guaranteed it will be well defined. So we define a new machine. Machine is slang for DFA. I don't know why I wrote machine, because DFA is fewer letters, but anyway, machine is slang for DFA. We define a new machine, which I will imaginatively call M prime. It has a new state set, a new initial state, of course, a new transition function, and a new set of accept states. So what's S prime? It's exactly the collection of equivalence classes of S. And what's S0? It's exactly the equivalence class of the old S0. What is F prime? It's the equivalence class of all those guys who are in F. It might be that you had two different things in F that turned out to be equivalent. So of course, they'll be lumped into one equivalence class. This is, for example, what will happen with S1 and S3. And finally, delta prime says, okay, I've got an equivalence class, and then I'm reading a letter. I should go to a new equivalence class. And this new equivalence class is the equivalence class of delta SA. Whenever you see definitions like this, what have you done? You've kind of gone inside the equivalence class. You've chosen one element. You've used that to do the transition, and then you've taken the equivalence class of the whole new thing. And then you have to ask, what if I had chosen something else? Well, lemma A says it doesn't matter, because anything equivalent to S will take you to the same equivalence class. So that's a well-definedness thing. That's why we prove lemma A. Okay, everybody with me?
There's a question in the chat asking if lemma A, if the opposite is true also.
If
Like the opposite direction of lemma A.
if delta PA, no, certainly not. Please find a counterexample. Okay. Now, I will state a lemma B. Supposing P is an F, and P is actually equivalent to Q, then Q must be an F. Okay, this is also clear. Even in my notes, I say do it yourself. That's kind of obvious. If Q is not an F, then they disagree on the empty string. So definitely they can't be equivalent. All right, lemma C. This says for every word in sigma star, if I look at delta prime star, so remember star always means the extension to words from single steps. So delta star of delta prime star of PW is equal to the equivalence class of delta star of PW. Okay, so this is this proof is by induction on the length of W. Okay, I leave it to you. I actually did it in the notes. Good. So there we are. We have this new machine. We proved these three lemmas. And now the theorem, the language of the machine M prime is equal to the language of the machine M. And maybe this proof I will do for you. Do to you. Okay, do for you. So supposing I take a word in the language of M prime, then you're in the language of M prime by definition. If delta prime star of the equivalence class, oh dear. Of the equivalence class of S0 on X is in F prime. That's simply the definition of the language. But this happens only if delta star S0X is an F prime. That's lemma C. And this happens only if delta star S0X is an F. That's lemma B, and the definition of what F prime is. And finally, of course, that is just saying X is in the language of M. Okay, so these two machines have the same language. And obviously, this machine M prime is smaller because I've replaced the states of the original machine by equivalence classes. So there have been some kind of collapsing. I've made a quotient construction. Okay, so it's got to be small. It might be that every equivalence class contains only one element. So it hasn't gotten really smaller, but maybe not. Maybe some of those equivalence classes contain several states. And so I did get a smaller machine, but for sure I didn't get a bigger machine. So when am I going to not get any non-trivial collapses? When the machine I started with is already minimized. But the example machine that I started with is clearly not, and it's very easy to see that this equivalence relation exactly reduces it to the three-state machine. Okay, so the machine, so we call this process collapsing, because you took a bunch of states, merged them into one state. So this collapsed machine is exactly recognizing the same language as the original machine. So we now have the task of designing an algorithm to minimize a deterministic finite automaton. And the basic idea is called splitting. So what we do is we pretend that all the states are the same. We just say, hey, there's one state. Everything is equivalent. Then we look at it and we say, no, 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 no. That can't be, because some of them are accept states and some of them are not accept states. So right away we split them and say, all right, the accept states are in one cluster, the not accept states are in another cluster. Then we look at it again and we say, wait a minute, look at these two states in the same cluster. This one takes an A into an accept state. This one takes an A into a reject state. So they can't be equivalent. So we keep splitting it like this. And when we can't split anymore, we stop. And the claim is this is actually the minimal machine. And why is it the minimal machine? Because we started out with everything clustered and we only split when we were forced to, and we saw something in the structure of the language that forced us to split those states. So we only did the minimal amount of splitting. So the algorithm looks like this. So this is called the splitting algorithm. So we're going to write P bow tie Q if there exists W in sigma star such that, whoa, this thing slipped out of my hand. No. Such that delta star PW is in F and delta star QW is not in F, or vice versa. That means delta star PW is not in F, but delta star QW is in F. In short, P and Q are not agreeing on what to do with F. This is just a negation of our equivalence relation. And now somebody asked a very interesting question about whether the equivalence was preserved by transition. No, by backward transitions, but the not equivalence certainly is. So fact, which you can convince yourself of. If there exists A in sigma such that delta PA bow tie delta QA, then P bow tie Q. So here's the algorithm in outline. I've given it in slightly more detail in the notes. So you define an S by S array of Booleans. Okay, so step one, for every pair, such that P is in F and Q is not in F, put 0 in the PQ cell of the matrix. So first of all, note that this is an equivalence relation. So we don't really have to keep the whole matrix. We only need to keep half of it because it's going to be symmetric because equivalence relations are symmetric. So you notice this is a matrix of Booleans. Matrices of Booleans are very interesting things. Just as you can multiply matrices of numbers by using multiplication and addition, you can multiply matrices of Booleans by using and or in exactly the same way. That's called Boolean matrix multiplication. And in fact, anytime you have a ring, you can define matrices over that ring using the two operations of the ring, and the collection of n by n matrices over a ring is also always a ring. So the Booleans actually form a ring. You can think of it as a ring instead of a Boolean algebra. And you can make matrices over that Boolean ring. And these Boolean matrices are amazing things. Okay, so that's just the initialization phase of the algorithm. So we've got this n by n matrix, and we put we put zeros everywhere where we know they can't be the same. So basically a 1 is going to mean, yes, these two guys are equivalent. But we don't know which guys are equivalent. We can only know which guys are not equivalent. So we're going to say, we're going to mark things that are not equivalent. Okay, so step 2 is a loop. Repeat until no more changes. Okay, and what do you do? So for each pair, PQ with, each pair PQ that is not already marked with a 0, check if there exists an A in sigma such that delta PA, delta QA is marked with 0. If so, mark PQ with a 0. And once you've gone through all the states, go again, because some of the new zeros that you've induced will induce yet more zeros in the next phase. So you keep doing this until you see nothing is changing anymore. Okay, so my notes actually contain an explicit working out of this algorithm for the 6-state machine, which I don't want to repeat here. because it's just a mechanical process of running the algorithm, but it is worked out there. So please look at those notes if you want to see the algorithm in action. Now, this is a mathy style serious class, right? So we don't just write down algorithms and say, yeah, they work. We prove the correctness of them. So I'm going to state a theorem, and I'm not going to prove it. If at the end two states are not marked 0, then they are equivalent. Okay, so there is a proof. This is not an obvious thing. There is a proof. I'm not going to write out the proof here because it's written in the notes, but let me tell you the key idea, which is almost the actual full proof. So supposing this theorem is not correct, what does it mean that it's not correct? It means there is some pair PQ such that they are not equivalent, but the algorithm failed to mark it, right? That's what would mean for the algorithm to fail, because the algorithm, the theorem says, if the algorithm didn't mark it, it's because they were in fact equivalent. So we'll call every such pair of things that are really not equivalent, but the algorithm missed them, we'll call them bad pairs. Okay, a pair is bad if they're really not equivalent, but the algorithm didn't find it. Good. So now we say, look at all the bad pairs. For each bad pair, there is some string such that one of them ends up in an accept state and the other one does not. Okay, so for each bad pair, there must be a witness, might be lots of witnesses. So you look at all the pairs and all the witnesses, one of these must have the shortest possible length of witness. So there must be one bad pair such that its witnessing string is the smallest possible. Okay, good. But now you take the first step from that witness, take the first letter from that witness, and you look at the two next states that you get to. Now the two next states better be distinguished or better not be equivalent, right? Because if they were equivalent, then of course this is not going to be a distinguishing string. So those two are not equivalent. And how do we distinguish them? Well, we look at our witnessing string with the first element deleted. Furthermore, this new pair also has to be a bad pair, because the algorithm says if after one step you see that there's a pair that's marked, then you should have marked this one. So if you had the two states that were not marked and you found two things that go to the next state and they were marked, then you would have marked this one. So then those two must also not have been marked. So that's also a bad pair. And it has a shorter distinguishing string. But this is a contradiction because we were supposed to have chosen the bad pair with the shortest distinguishing string. So this contradiction shows there can't be any bad pairs. It's kind of a descent argument instead of an induction argument. Okay, so this is the proof that this algorithm actually correctly produces the, correctly calculates the equivalence relation, and therefore you can safely compress the states into these equivalence classes. So let's analyze the running time. So this is an order n to the 4 algorithm, where n is the number of states. It's very naive. There are all kinds of improvements. So some basic data structure hacking will get you to n squared k using some basic data structures. But then there's a quite clever algorithm due to Hopcroft, which is n log n. Now, Hopcroft's algorithm, it's based on the same idea. He just does everything more cleverly, but the same fundamental idea. You're still splitting the state space. And I'm not going to show you Hopcroft's algorithm because it's just algorithm hacking, but it is somewhat clever, of course. There is an algorithm due to Brozovsky, which is exponential. And because it was exponential, everybody said, what a silly algorithm, and they didn't pursue it. But in fact, this is one of those things where the theoreticians don't tell you. They always tell you, yeah, worst case analysis, this is the gold standard for algorithms. And yes, it's true. Don't tell them I'm telling you rebellious things like this. But the fact is, Brozovsky's algorithm, though exponential in the worst case, actually works really well most of the time for automata that you find in nature. So second half of this class is about Brozovsky's weird magic algorithm. It's completely black magic. And why it works was only, well, Brozovsky proved that it worked, but somehow the deep insight as to why it really works was provided years later by various people. But that's what's described in this paper that I linked on the web page. So how are we doing on time? We traditionally stop at 11:30, but I think I'm going to keep going till I finish Myhill-Nerode.
What's k in O n squared t?
K is the number of, I think it's the number of transitions. We put this for, oh, sorry. Yes, so you have to maintain a list of pairs that are distinguishable. And, sorry, K is the size of the alphabet. K is the size of the alphabet. Now, I'm sure there's a question in Maria's mind that she's not asking, but the question probably is there a unique minimal automaton? And the answer is yes. There is a unique smallest DFA to recognize a regular language. This is a fantastic result, not very difficult, but it's pure algebra. So this leads us to the next topic. It is called the Myhill-Nerode theorem. And it was proved in 1957 independently by John Myhill and Anil-Nerode. Anil-Nerode is an amazing dude. He proved this in 1957. He was a big name in mathematical logic, and he's still alive and he's still active. He's like 90 something. still a prof at Cornell, and my Facebook friend. Anyway, poor John Myhill is dead. Anyway, Myhill-Nerode theorem. So the Myhill-Nerode theorem is in these notes, which I put on the web page. So I will again, it spells out a lot of details that I'm going to just say very quickly right here, not necessarily even writing everything down. So it starts out by explaining what is a monoid all over again and what's an equivalence relation. So we're going to start out with a specific kind of equivalence relation on sigma star. So Stefan, are there any pressing questions on the chat?
Are there minimal automata with non-trivial automorphisms?
No, I don't know what non-trivial means. Because an automorphism is going to preserve everything, yes? So the only automorphisms are going to be, I changed the names of the states. So if you consider that to be a trivial automorphism, the answer is no. There are no non-trivial automorphisms. This is actually also addressed in my notes. So up to what name I gave to the states, this is really minimal, unique, minimal. And by the way, this is the way you test equality of regular expressions. You take two regular expressions. There's a systematic way of constructing an NFA from a regular expression, as we saw in the proof of Claney's theorem. You determinize it, as we saw yesterday. You know how to make a deterministic automaton from a non-deterministic one. This might cause a huge amount of blow up, but then you minimize it. And that's unique. And now if your two regular expressions produce, isomorphic DFAs, and the isomorphism concept is an extremely trivial one. It just says it's identical up to renaming the states. And only then do you have the same language described by that regular expression, by those two regular expressions. So even though regular expressions look like they have a cool algebra and a lot of equational stuff you can do, actually anything algorithmic you want to do with them goes through automata theory and not through the algebra of regular expressions. Who asked about non-trivial automorphisms? Come on out of the
Stephen
woodwork.
Fay.
Who?
Stephen Fay.
Right. So I guess you're thinking about automorphisms of graphs.
Yeah.
Which might be indeed a very interesting structure. But these things are so rigid. There's it's isomorphism of automata. Okay. So definition. We will say an equivalence relation on sigma star is said to be right invariant if for all x, y in sigma star, it implies that for all z, for all xy in sigma star, let me give a name to this, an equivalence relation R on sigma star is said to be right invariant if for all xy in sigma star such that x is related to y, it implies that for all z in sigma star, xz is related to yz. So you see why it's called right invariant, because you can stick anything on the right-hand side and the equivalence will be preserved. Okay. So no matter what we stick on the right-hand side, if X is related to Y, then by sticking Z on the right-hand side of both of them, that equivalence is preserved. Of course, not every equivalence relation has this property. Some of them do, some of them don't. So we're going to look at two very important equivalence relations that do have this property. Okay, so example 1. So this, by the way, is actually an example of some importance. It's not just an example I'm showing you to illustrate the idea. This example plays a role in the Myhill-Nerode theorem. So supposing I have a DFA M, and it consists of some states. There's an alphabet, start state, transition, which I can do a better delta than that, and a set of final states. So I'm going to define an equivalence relation. I'm going to say X. I'm going to define a relationship called R sub M, which is based on this machine M. I'll say R sub M, X is R sub M related to Y, if and only if delta star Q0 X equals delta star Q0 Y. They both take the start state to the same place. Easy to see that this is right invariant, because once you've got to the same place, it doesn't matter how you got there. You stick any Z you want, it's deterministic, so its subsequent trajectory is fully determined. Okay, so it's easy to see that this thing is right invariant. Okay, so I actually say more words in the handout explaining exactly why this is, but to you it should be obvious that this thing is right invariant. So I'm going to define another example of a right invariant equivalence relation. So this one you see is, you give me a machine and from it I constructed the right invariant relation based on what these things do to the machine. Now I'm going to construct another one based on a language. Given L in sigma star, not necessarily regular, we define R sub L on sigma star as follows. X R sub L related to Y if and only if for all Z, X Z is in L, if and only if Y Z is in L. And this one, almost on the definition, you can see has to be right invariant. So we want to prove that if X is RLY, then XZ is RLYZ. Well, you stick any U after XZ, then you've got XZU is in L if and only if YZU is in L. That's what we want to prove. But I can regroup it and say XZU and YZU. And because I had a universal quantifier in the definition of RL, so X ZU is in L if and only if YZU is in L. But this is the same thing as saying XZ and YZ are RL related. So essentially, a trivial argument shows that this thing is also right invariant. So just some terminology. If we have a set S and an equivalence relation tilde, then the index of this equivalence relation is the number of equivalence classes. Of course, the number of equivalence classes might be infinite, in which case we'll say, hey, it has infinite index. Or it might be finite, in which case we say the index is whatever that finite number is. So for example, if I look at the integers and I define two integers to be equivalent, if they are equal mod 5, then of course, this is an equivalence relation and its index is 5 because there are exactly 5 different equivalence classes. Each equivalence class is itself infinite, but the number of different equivalence classes in this example is finite. So please don't confuse an equivalence class being infinite with the number of equivalence classes being finite or infinite. Okay. So the proof that these two equivalence relations are in fact right invariant, I think probably obvious to you, but if not, it's spelled out in the notes. But now I want to state and prove the main thing today, which is the Myhill-Nerode theorem. And they stated it in an odd way. Because the important consequence of the Myhill-Nerode theorem is that there is a unique minimal automaton. But that's not what they say. They say something, and you have to look inside the proof to say, because of the way this is proved, it implies that there is a unique minimal automaton. So the theorem doesn't say there is a unique minimal automaton, but that is the most important consequence. So the theorem says TFAE. Everybody knows what TFAE means? The freaks are everywhere. No, sorry, it doesn't mean that. It means the following are equivalent. Okay, the following are equivalent, and it's kind of convenient. So sometimes you have a bunch of things and you want to prove that they're all equivalent. And so you state it like that. The following 3 things are all equivalent. And if you state it like that and you arrange them the right way, you can prove the equivalence by proving 1 implies 2, 2 implies 3, and 3 implies 1. So that cuts down your proofs into 3 cases instead of 6. Otherwise, you'd have 3 pairs. Yes, so the following 3 statements are equivalent. 1, L is regular, i.e. recognized by a DFA. 2, L is the union of the equivalence classes, of some of the equivalence classes of a right invariant equivalence relation R of finite index. So any equivalence relation breaks up sigma star into disjoint sets called a partition. So what this thing is saying is you have some equivalence relation of finite index, and this equivalent relation is right invariant. And if you take some of these things, you will get exactly the language L. So given the L, you can always find such a relation with this property. And 3 says any equivalence relation R with the properties described in 2 that means it's right invariant, it has finite index, and L can be constructed by taking some of the equivalence classes and unioning them. Has to refine RL. So before I start the proof, I want to be sure that everybody understands the words I'm using. So, well, the one key word is refine. Is everybody clear about this word? What does it mean for an equivalence relation to refine another one? If not, ask me now.
What does it mean?
Ah, good question. Was that Omar?
Yeah.
Good, Omar. You asked the question that 25 other people wanted to ask. Okay, let's see. So let's say I have some, I'm going to draw a figure, then later on erase it because it's just a scratch. So I have some set like this, right? And then I have an equivalence relation, whatever it is. And what is an equivalence relation to? It breaks up any set into disjoint pieces. Okay, so you see these green lines, they divide up my set. You cannot have two equivalence classes that are partially overlapping. They're either disjoint or exactly the same. So you've broken it up into a disjoint family of sets, and together all these sets cover the whole space. Or in this case, they cover all of sigma star. Okay, so that's what the word partition means. And we know equivalence relations and partitions are equivalent concepts. If you give me a partition, it automatically defines an equivalence relation by saying two guys are equivalent if they're in the same set of the partition. So sometimes these things are called blocks, the blocks of a partition. So supposing I have a different equivalence relation, it might be completely different. I'm looking for red. Do I have red? What is this color? Ah, that's not red. What is this? Blue. Okay, that'll do. So supposing I have a completely different equivalence relation, it will also divide up the space into blocks, disjoint sets that cover the whole space, a different partition. But to say that it refines it means the blocks of one all totally fit inside the blocks of another. So if we have, oops, I seem to have zapped. the outer black line. Okay. So here we have the set, and it's partitioned by the green equivalence relation. So now, if I have a blue equivalence relation that breaks it up into blocks, it might happen that the blue blocks all live completely inside I'm showing little gaps, not to suggest that there are actual gaps, but just to show you that these blocks are disjoint from each other. There's nothing in between. It could have some of the blocks exactly matching. And other blocks not. But in every case, you see a block of the blue partition is completely sitting inside a green block. So you understand this concept? You've taken the blocks, the green blocks, and broken them up further. What you have not done is had blue blocks that go partly from one green block into another one. Okay, that could happen with some equivalence relation, but then we won't say that it refines it. But here we'll say it refines it because it says fewer things are equivalent. So look what it means when you have refinement. It says if you are related by the blue relation, then you have to be inside a blue block, and every blue block is sitting inside a green block, so you must be related by the green relation. Okay, so that's what it means to be refined. What else can we say? The index of the green relation has to be smaller than the index of the blue relation. There have to be fewer blocks because the blue one is obtained by breaking the green blocks into smaller pieces. So what we're saying in part 3 of the Myhill-Nerode theorem is that the coarsest equivalence relation, the one that produces the fewest blocks, is this one coming from RL. And RL is canonically defined. Right? It's just defined from the language. It has nothing to do with the choice of automaton. We're going to prove the equivalence of these 3 statements. Can I erase this picture now? No dissent? We're going to prove 1 implies 2, 2 implies 3, and 3 implies 1. And with the way we're going to prove 3 implies 1 is we're going to construct from RL an automaton, right? Because 1 says there's a DFA to recognize L. And because of 2 implies 3, we're going to see that, 1 implies 2 is going to start out by saying, here's an automaton to recognize L. I'm going to construct a right invariant relation from it. 2 implies 3 is going to be the interesting argument, which is what I will do in detail. 3 implies 1 is going to be, hey, I'm going to construct an automaton from RL. And the fact that 2 implies 3 means any automaton that you get is going to induce some right invariant relation, and that is going to have more blocks than the one you get from RL. So the one you get from RL has to be the smallest over all possible automata. So that's the way in which the Myhill-Nerode theorem tells you there is a unique smallest automaton DFA to recognize a regular language. Okay, so let's go. And because I've written this thing out in the handout in complete detail, I'm going to do this very fast and just tell you ideas here. So 1 implies 2. Okay, so construct. So 1 means I've got a machine. we have M with the language of that machine is the L we're looking at. Construct RM as in example 1. Okay, we've already seen that this is right invariant. And now define S sub Q to be the set of X such that delta star Q0 X equals Q. Okay, and now L is just union over Q and F S sub Q. So S sub Q is actually exactly the set of words associated with the equivalence class of the state Q. So every state actually defines an equivalence class. And clearly, this language is precisely the union of some of those equivalence classes, namely the ones that correspond to the except states. So we started with a machine, and that was what we got to assume in 1, that there is a machine to recognize L. We constructed the RM as an example 1, and we observed that it is right invariant, and the language L has to be the union of equivalence classes. 2 implies 3. So we have R. So now there's no machines in the picture. Somebody has just given us an R, and they've said this R is right invariant. So R is known to be right invariant. It is an equivalence relation that's just taken for granted here. R has finite index. By the way, how did we know that the thing constructed in 1 implies 2 has finite index? Because it's a finite state machine. So R has finite index, and L is the union of some of the equivalence classes of R. So all this we get to assume. And now we want to show if X is related to Y, then X is RL related to Y. Why does that prove refinement? Because it tells you that the blocks of R are all sitting inside the blocks of RL. So this will complete 2 implies 3. Now, suppose X is in the language. Then X is inside some equivalence class of R. Okay. Now, so that's just a fact. So now suppose that X is related to Y, and XZ is in L. Okay, then XZ must be in some equivalence class of R, and this whole equivalence class has to be in L, because L is the union of the equivalence class. So you can't say, I'm going to take half this equivalence class and reject the other half. You have to take the whole equivalence class or none of it. So this whole equivalence class to which xz belongs has to be in L. Since R is right invariant and X is related to Y, then XZ has to be related to YZ. So YZ is in the same equivalence class of R as XZ. But we said that whole equivalence class is in the language. So YZ is also in L. And you can argue similarly with Y and X interchanged. So in short, what have we shown? For all Z, XZ is in the language if and only if YZ is in the language. But this is the definition of X RLY. So 2 implies 3. Okay, so 3 implies 1 is straightforward. Construct an automaton from the equivalence classes. Of RL. Okay, I'm not writing out details here. Details are in the notes, but they're just like things we've done before. For example, when I did the minimization discussion, I showed you how you take a quotient automaton and build a new one. So details in the notes. So 2 implies 3 shows that the automaton constructed in the proof of 3 implies 1 is the unique smallest DFA to recognize L. Okay, I will stop here for, let's take a break till 12:15. And then I have 40 minutes to tell you the sketch of ideas of Brozovsky's algorithm and the beautiful theory of duality. So some people had some questions about automorphisms. That's also addressed in the notes. It's actually kind of a trivial point. You can define the notion of homomorphism between automata, which I've written and defined in the notes. And, and then isomorphism means the same, what you would expect. Bijective homomorphism whose inverse is also a homomorphism. And you can prove that homomorphic automata always recognize the same language. And Myhill-Nerode is basically showing uniqueness up to isomorphism. But the isomorphism here is pretty much just I get to rename the states. So instead of calling them S0, S1, S2, I can call them Q0, Q1, Q2, and say, oh, it's a different automaton. But you see, it's not different in an interesting way. Okay, break. Anybody have any questions? Yes, Stephen.
I have maybe quite a naive question.
Those are the best ones.
Okay, so you mentioned that uh, we can think about modding by equivalence relations as homomorphisms.
No, I didn't say that. I said you
No?
can find a notion of homomorphism.
Okay.
And then, yes, so the map from an automaton to its quotiented one will indeed turn out to be a homomorphism. That is correct. But the notion of homomorphism doesn't only come from that. I can define homomorphisms between all kinds of automata.
Okay, so are there rules of like kind of like of divisibility? Like let's say I quotient by the equivalence relation. Will then the number of states that I end up with be a divisor of the number of states I started with?
No.
Okay.
So all of you, so Maria asked me questions like this before. You're all very much influenced by group theory, where
Uh-huh.
of course such things happen, but not here. It should tell you what an amazing subject group theory is to give you such powerful results like Lagrange's theorem.
Hmm.
But no, you can easily construct examples where you see what will happen is that I can make up an automaton in which, these 11 states get collapsed into one, and then that state doesn't get collapsed at all.
Oh, wow.
So there's nothing like these numerical relations that you were perhaps hoping for.
Okay, so there's no real way of like looking at an automata, like, and even just, let's say if there's no significance behind, like, let's say if there's a prime number of states or something, or like
Prime, well, no, but it's not as if there's no algebra in it. There's a lot of algebra in it. So there's some so there's a whole subject called algebraic theory of automata, of which Myhill-Nerode theorem is kind of the first baby step, but the subject is vastly more general than that. And I'm not really going beyond into it, but you do have results that say every automaton is the homomorphic image of certain prime automata. Okay,
What?
they're like certain prime automata, and every automaton can be constructed by taking a certain kind of product called a Reith product of these prime automata and then quotienting it. So this is a bit like Jordan series and group theory, a bit like. But anyway, so you might ask, so what are these prime automata? Well, it turns out from every automaton you can construct a certain monoid by quotienting it by this equivalent sub L. Yes, and you get a certain monoid called the syntactic monoid of a language. And it turns out that the syntactic monoid, so this was one of the grand theorems of algebraic automata theory. The syntactic monoid is the quotient of a Reith product of any finite group or two specific non-group monoids.
What?
So there are two particular monoids that are not groups, and apart from that, you're allowed to take any finite groups you want, make Reith products, quotient it, and you'll get all automata this way. So this is one of the grand theorems of automata theory. It's called the Krohn-Rhodes decomposition theorem.
Wow.
So it is I mean, it takes a long proof, but it's telling you there is some kind of structure theory. It's not just we draw circles and lines and get a god-awful mess. But yeah, I mean, things like Lagrange's theorem, that's a fantastic thing, right? Because it tells you, oh, well, the size of the cosets are all the same. We have nothing like that here, no. I do remember how excited I was when I was a little boy learning Lagrange's theorem the first time.
Yeah.
I still have the book from which I learned it, and I had penciled in the margin, oh wow, right next to Lagrange's theorem. But I don't want to say sadly it's not true here, because it's not sad. There's other different structure, very interesting structure at that.
Can I ask another kind of little bit unrelated question?
Is that Haneli?
Yeah, it's Hanley.
Haneli,
We've been
why can't I see you?
because I'm using an archaic computer and my camera doesn't work.
Ah, okay, all right,
I have the same issue.
okay.
That's a 2013 computer. You can't expect much out of it.
Mm.
But I have a quick question. We've been studying those properties under set theoretical approach. Is there any theory for automata that's more related to a topological perspective, the topology perspective of it?
Oh my God. You asked the wrong person. Now you have to tie me down and stop me from talking all day because, yes, I'm just writing a paper on topological automata.
Oh, that's cool. I mean, I could see the same thing we have in type theory. I could see the same relation for automata, and
Yes. Well, you know, type theory is just another language for category theory.
yeah.
So we can study categories of automata. So if you look at my Myhill-Nerode notes, and if you look at the very last section, it says, do not read beyond this, I mean it. So if you read that.
Well, I followed the instruction and I didn't read beyond it.
Oh, you're never meant to follow instructions, come on. So in fact, this paper, which I've linked, is all about categories of automata, and it shows that you can do automata in the category of vector spaces. They're actually very useful and important. They're called weighted automata. You can do categories in the, you can do automata in the category of topological spaces, sure. Compact Hausdorff spaces, in fact. You can do lots of things, yes. Rosie is an expert, by the way.
Or would you just be defining the automata, the category of the automata axiomatically based on like similar axioms to the ones you use to define those other categories, or do the automata themselves somehow have some structure related to those objects you're talking about?
The automata themselves have some, I'm actually going to do something like this right after, in 6 minutes, in fact. So if you hold your horses, I will tell you about a more general concept of automata. But yes, Haneli's question is a brilliant one. It's all very much based on sets, and you can actually lift it. So what happened was Brzezinski came up with this black magic algorithm. And people said, what a weird algorithm. How on earth did he come up with this? What does it mean? And years and years and years later, I understood how to explain it as a duality phenomenon. Actually, what happened was I invented it myself. And then somebody told me, oh, this has been known since 1962. But then the way I invented it was very much based on modal logic. And then I showed it to, started giving talks on it. And then other friends of mine said, but the right way to explain that is categorically. So now it took about 20 years to write this paper, but it is now coming out. So the paper on the website is from 2014. And it gives some ideas. The one that's coming out one of these days soon is much fancier, with more fancy examples. So, you know, people in control theory, of course, don't study automata, they study systems of differential equations and stuff like that. And that can be put in the same categorical language and viewed as automata-like things, and you can do minimization there.
Yeah, I recall seeing some connection between automata theory and dynamic systems.
Yes.
There are people doing that. I remember this thing, but this whole universe of putting category theory into more applied sections of engineering, there are not many people trying to do that.
More and more. So there's a guy at MIT called David Spivak who does that. There's a guy, well, there's a seminar going on called Applied Category Theory.
Yeah, from MIT. I'm following these lectures.
No, from UC Riverside.
Oh, there's also the category theory seminar from MIT.
Yeah, that's run by David. But the one from California is run by John Baez. So I think the one from California is a seminar and the one from MIT is a class.
I think the one from MIT is like mixed, because I recall seeing lectures and seminars.
Okay. Anyway, I gave a talk in the one from Riverside in which I showed how to do probability theory categorically.
Is it recorded? Can we see that?
Yes, on YouTube.
Oh, I'm gonna search for it. Thank you.
You just go Panang Garden, conditional expectation, Riverside. You should find it on YouTube. But don't watch it now because I'm about to start in 3 minutes.
I just added to my watch later.
Did you find it?
Yeah, it's the first thing that shows up.
That was my first Zoom lecture on April 8th. But I used slides that were pre-prepared, not like this where I'm.
I'd like to welcome.
Hello?
Yeah, I found it. I'm gonna share the link if somebody else wants to see it.
Yeah. Oh, I see. What we heard was the first.
Yeah, the first second.
Yes. Okay. Is everybody back? I guess the people who are not back can't say, no, I'm not back. So it's kind of, I know what, I'll take a 2-minute break. So, because I've been sitting all this time. Somehow, everybody's camera seems to be off. Is that correct? Show grid video. No. Some cameras are on, but when I go to thumbnail, I don't see anyone. Okay, maybe I'll just switch to gallery. When I go to gallery, I see all kinds of people. Right now, I'm seeing Marcel, Rahul, Anna, Rosie, and Maria. But when I go to thumbnail, I don't see anyone with an on video. So I don't know why it does that, but all right.
You can click on the 3 dots and hit hide non-video participants.
Which 3 dots?
Like on any of our video, there'll be like 3 dots on the top right in blue.
Okay.
If you click that, there'll be an option for hide non-video participants.
It says pin video, spotlight video, make host, allow record, remove, rename, put in waiting room.
Oh, not on your own. Click on any one of us.
Yeah, I'm clicking on yours. It says
For me, it gives me an option.
doesn't give me. Allow record, remove, rename, put in waiting room, make co-host, make host, spotlight, pin, chat, stop video, mute audio. Okay, anyway, as long as I'm seeing some faces, we can rock and roll now. Right, here we go. And now I've told you there's an n log n algorithm for minimization. So why the hell would anybody look for an exponential one? But anyway, that's what Brzezinski did. So poor Jan Brzezinski died only a year or two ago. So he was the thesis supervisor of one of my colleagues at McGill, Denis Terrien, who has since left academia and started working for Element AI. But for many years, he taught Comp 330, and it was only when he became head of department and stopped teaching classes that I got to teach it. So he is the master of using automata theory to prove things in complexity. His advisor was Jan Brzezinski at Waterloo, and Brzezinski came up with the following insane algorithm. So Brzezinski. I'm sure I'm not pronouncing it correctly. I think it's Brzezinski. Brzezinski's algorithm. Okay. Take the DFA and, well, take the DFA seems to be a stupid thing to start with. So you've got a DFA. What do you do with this DFA? Reverse all the arrows. Just you've got an arrow pointing from A to B like that.
Professor, we are not seeing what you're writing.
You're not?
No.
Yes, why is that not happening? I can.
It's happened to me before when I was also lecturing. You have to stop the
and restart.
sharing and restart it.
Okay. Okay. Zoom is not perfect. iPhone, iPad via AirPlay. Share. Okay. Now do you see it?
Yes, now it works.
Very good. Thanks, Justine. So reverse all the arrows. So you've got an automaton. What do? You take it and you just reverse all the arrows brutally. So reverse, I mean literally, you take the arrow and draw it backwards with the same label, right? And of course, it may happen that in your automaton, you've got something like this going on. So of course, if you're looking at the reversed automaton, even though your original thing was a DFA, your reverse thing will be an NFA, right? So reverse all the arrows and change the initial state, the start state, to an accept state, and make all the accept states start states. So basically, it's already become an NFA because you've got non-determinism in the transitions. And in an NFA, you can have multiple start states. So this is now totally an NFA. To determinize it. Right? By using the subset construction we talked about yesterday. You might end up with some states that are not reachable. By reachable, I mean there's nothing that will get you there from the start state. It could be that you have some random states that nothing connects to it. So these are called unreachable states. So we remove unreachable states. Because obviously, if they can't be reached, they're not playing any role in language recognition, because the whole notion of recognition is you start from the start state and then you end up in an accept state. So if there's a state that you can't get to from the start state, forget it. It can't be part of you. It's not doing anything for you. This step, determinize it, this may well cause exponential blow up, right? Because you're looking at the set of all subsets, and it is actually possible to give examples. And then step 4 is repeat 1. Step 5 is repeat 2. And step 6 is repeat 3. Okay, so step 2, you remember, produced an exponential blow up. Step 5, double exponential blow up. At least that's what you expect. Black magic. Double exponential blow up doesn't happen. In fact, you get the minimal automaton. So instead of getting a blow up completely out of the blue, you get a massive collapse, because you already blew it up a huge amount in step 2, but then you've collapsed it not just to the collapsed version of the blown up machine, but you've got the minimal version of the original machine. Okay. The result is the minimal machine. This deserves multiple exclamation marks. Indeed, there's exponential blow up in the middle. So even though you got to the minimal machine, worst case analysis tells you this is a very bad algorithm. And people said, how weird, very interesting, but obviously not practically useful. But it turns out that if you look at this categorically, this is a super good minimization algorithm for other categories than set. So in particular, it's the preferred minimization algorithm for weighted automata, which is basically automata theory happening in the category of vector spaces. So I don't think I can explain everything. This whole part of the lecture is just to get you interested and excited with some ideas. If you really want, you can read all 30 pages of this paper, but I'm just going to sketch some ideas. Let me see, what have I got here? All right. Now, Brozovsky gave a proof, of course. So, but this proof was like, yeah, this happens and that happens. And then in the end, yeah, it's minimal, but then it's still like, why did this thing even work? And years later, so he did this in 62. I guess the paper may have come out in 64. I think in early 2000s, I started working with 2 young profs in our department who were studying PSRs. Now they're not so young anymore. They were Joel Pino and Doina Prikup. And we were looking at minimization. Well, we weren't looking at minimization. We were looking at trying to understand Markov decision processes and how they work. And out of the blue, I invented a minimization algorithm. And basically it was this one, except it was in the context of MDPs and not in the context of automata. So that's the first clue that these ideas apply more generally. Okay, enough history lesson. Let us try and explain what is an abstract notion of an automaton. Okay, so I'm going to define an automaton by describing certain functions, but then I can write these functions as a diagram. So let's say X is the state space of my automaton, and A is the alphabet. Okay, now this notation X raised to the power A simply means the set of all functions from X to A. Okay, X raised to the power A means the set of all functions from A to X, not X to A to X. Okay, so this is another way of writing this set of functions from A to X. Okay, delta. So what is an automaton? It defines a map from X to the power A. How does it do that? So delta of X is supposed to give you a function from the alphabet to X. So let's apply it to a letter in the alphabet. We should get a new state. So this is, you see, just a different notation for writing delta X comma A. So this process, so instead of writing it as a map from X cross A to X, we have rewritten it as a map from X to the A. This process of converting a function of 2 arguments into a higher order function of cascaded arguments is called currying. So all I've done is I've curried the transition function and reinterpreted it this way. Let me delete all this junk. Right, so that's the transition function. So what else is there in an automaton? There's an initial state. So I have to tell you, hey, this state is special. It's the start state. How do I describe that? By drawing a map. 1 stands for the 1 element set. So there's a function called I. It goes from the 1 element set to X. So what does such a function do? It basically points at 1 element in the set and says, you are it. So this is a way of choosing a state or designating a state in X. And this is going to be our start state. So this letter I is supposed to suggest initial state where we start from. Then what else is there in an automaton? There are a set of accept states. Sometimes these are also called final states. How do we tell you what are the final states? It's a map from X to the 2 element set. So you can think of this 2 element set as true, false, or yes, no. And basically all the final states get mapped to yes or true. All the other ones get mapped to false or no. So to describe a subset of a set is just a map from X to the 2 element set. So this you know very well also, because this is just a characteristic function of a set. So this little f is a characteristic function of the subset of final states. So I've picked out an element. I've picked out a subset of final states. I've described a transition function. This is an automaton. And you see I've described it with arrows alone. So now you can see I can do this in any category. I can say, oh, I've got a vector space. I've got this kind of product space. I've got the terminal object. I've got a 2 element space. I have maps like that. And that's an automaton in whatever other setting I want, probabilistic automata, vector spaces, topological spaces, etc. Okay, but for the rest of this discussion today, I'm staying in set. I'm just giving you a taste of how to do this more abstractly. So this is an automaton. Now there are two fundamental concepts that I need to talk about, and they are called reachability and observability. So by the way, I insisted that people had to ask for my permission to join this class. And I made everybody email me. And I kind of grilled you. It's because I'm expecting that you don't say, oh my God, I want every step of every discussion spelled out step by step, because I ain't going to do that. So, but it's going to be particularly sketchy now. So there are lots of things for which, if you really want to know, you have to read the notes. I want to tell you some key ideas. So even some notations I'm not going to necessarily spell out. Okay, I want to explain these two concepts. So I said these are all finite automata, but now I'm going to introduce two infinite state automata. And you might say, what the hell, infinite state automata? Those are wild and crazy things. Yes, they are, but these ones are very well structured and they have some amazing special properties. So this X guy, this is certainly a finite automaton, but I'm going to now introduce two different infinite state automata. One is going to be, one is going to have infinitely many states. The other one is going to have even more states. So the first one, I take as my state space A star. A is, by the way, what we've always been calling sigma so far. It's just that in this paper we use the letter A, and I'm sure I'll make mistakes if I try to do on the fly renotation. So A star is just the set of all words. Obviously, this is an infinite set. And I'm going to say, that's my infinite state automaton. So every word is a state. And what's the initial state? The empty word. So it's the map that goes from the one element set to this word epsilon. And I'll call the map itself also epsilon. Now, what's the transition? There has to be a map like this, which I will call alpha. So what does alpha do? Alpha maps a word to a function from A to words. So if you give me a letter A, it will give me the new word W dot A. So just a word with A stuck at the end. That's the transition function. Infinite state automaton, the states are words. What's the transition? Stick the new letter at the end of the word. Okay. Good. So now a thing that I'm going to just say without spelling out details. There exists a unique map R from A star to X such that the diagram above commutes. Okay, so let me show you this map. It goes like that. And this map is called R. And this map is called R superscript A. So does this paper carefully explain what R superscript A is? Okay, so maybe I should explain explain this in general. So first of all, I want to explain this phrase, a diagram commutes. So you see what's shown in this picture is a bunch of arrows representing functions. To say a diagram like this commutes, it means whatever path you follow and you compose the functions along that path, it's the same as if you follow a different path. So this means, for example, R sub A composed with alpha composed with epsilon is the same as going I delta. And similarly, going like this is the same as going like that. And going like this is the same as going like that. So every path of following these arrows, if you compose the functions along the path, it's exactly the same as following a different path between the same endpoints. So it's a way of stating a bunch of equations very compactly. Okay, so this one actually says there's one equation here, and one equation for the outer thing. So 3 equations are stated by just saying this diagram commutes. So I want to explain what this R superscript A thing is. So in general, supposing I've got a function f from 2 sets, from one set V to another set W, then I induce a function f superscript A, which goes from V superscript A to W superscript A. And what does it do? Supposing I take phi in V superscript A, then f superscript A applied to phi has to give me a function in W to the power A. So if I apply it to an element of A, I have to give you an element of W. Well, how can I possibly do that? Well, phi applied to A will give me an element of V, right? So once I have an element of V, I can apply F to it, and that will give me an element of W. So if you want, I can write it like this. Is the thing that maps A to. So that's how I lift a function from V to W to a function from V to the A to W to the A. Okay, so that's what I did up here. I had some function R, and then I get this thing there. Now, what is this R map? How do I get R? And why did I call it R as opposed to any of the other 25 letters in the alphabet? So if you look at what it says, this has to commute. So R maps the empty string to the initial state. This thing says, as I add a new letter, it should kind of match up what the transition is doing. So in fact, exactly what this thing is doing is saying, hey, track every word through the automaton with delta star. So basically, R applied to a word is delta star initial state W in our old notation. And you can check with this definition of what it means to lift R to the A that this diagram commutes. And you can also check it's the only thing that will work, because at each step I'm supposed to respect the transition structure. So letter by letter, I have to be tracking the transitions as dictated by alpha. The image of A star under this map are exactly the states that I can reach with some word. That's why R was called R. It's the reachability map. Is the reachability map. So it tells you which states of the automaton can actually be reached. Now, Uniqueness is not so difficult to see. We will say that an automaton is reachable if every state can be reached. So the automaton is reachable i.e. if R is surjective. Okay, so that was one of the infinite automaton. It has a special property. For every automaton, there is a unique map R such that this diagram commutes. And the image of that R map is the set of reachable states. And the map automaton itself is reachable precisely when R is surjective. Now I'd like to describe another automaton. So this one was countably infinite. This other one is going to be uncountably infinite. So even bigger. So you see, this automaton didn't actually have a notion of final state. It was just trying to track the transition structure. Didn't really have a notion of acceptance. This one is going to be analogous, but it's not going to really have a notion of initial state, but it is going to have a notion of acceptance. So it's 2 to the A star. So A star is, of course, countably infinite. 2 to the A star is uncountably infinite. And it's going to be backwards. So it's not going to have an analog of this one map, but it's going to have an analog of the F map. And this map, we'll call it epsilon question mark. So you see, what is 2 to the A star? An element of it is a subset of A star, what we've been calling a language. And we'll say L is an accepting language precisely when it contains epsilon. Okay, so that's what this epsilon question mark thing does. I have to give it automaton structure. I have to give you a map like this, which I will call beta. So how does beta work? Can I fit beta in here? Let's see. So beta takes a language, L, an element of 2 to the A star, and it gives you a map from A to the set of all languages. So if I apply it to a little a, I should get a new language. So what is this new language? It's the set of words in A star such that I look for the words that start with A that are in L and delete that A. So this thing is sometimes called the Brzezinski derivative. And it obeys, formally speaking, some of the rules of differentiation, formal rules, in fact, even including Leibniz's rule. So this is the Brzezinski derivative, and it defines an automaton structure. And just like there was a unique map going into every automaton from this guy, there's a unique map coming out of every automaton into this guy. And this map we'll call O, and over here there's an O superscript A. So the statement is there is a unique map O from X to 2 to the A star such that the diagram commutes. So what is this map and why did I choose to call it O? So of course, just in the same way that I lifted R to RA, I'm also lifting O to OA. So O maps a state in X to the language accepted if that state happened to be the start state. Ah, now supposing two states map to exactly the same language, that means you can't see any difference. So imagine that you can't actually see which state you're in. You just get to feed in words and then you get to say, did this word get accepted or not? And now you're doing experiments on this machine and you're trying to see, can I tell which state I'm in? Now, supposing there are two states such that they behave exactly the same way on every word and behave the same way means at the end they accept or reject in exactly the same way. And all you get to observe is I fed in a word and I got to wait and see whether it got accepted or not. And now you're trying to say, can I have guessed which state the machine started out in? Now, if there are two states in which they are exactly the same language, then there's nothing I can do to tell them apart. And so this map is called, O is called the observability map. Two states can be told apart exactly when OX is not equal to OY. So two states, let's say X and Y, can be told apart exactly when this map distinguishes them. And if two states cannot be distinguished, you might as well combine them. That was the essence of how we collapsed machines to get minimal machines. So we say an automaton is observable if any two states can be distinguished. And i.e., if O is injective. So you see, reachability means this map is surjective. Observability means the map O is injective. Now, the basic claim is a minimal automaton is reachable and observable. And essentially, the theorem that we proved in this paper is that there's a particular operation you can do, which actually has a nice categorical definition. It's simply applying the power set functor. And what you can show is the following. It's actually spelled out in some detail. We proved the following theorems. If x delta t, sorry, not t, I f is reachable, then the machine you get by taking the power set 2 to the x, 2 to the delta, f, and 2 to the I is observable. So that was the first part. The second part we proved was that if x delta I f accepts a language L, then 2 to the x, 2 to the delta, f, 2 to the I accepts reverse L. And this is simply the language you get by reversing everything. So you take the language L, you take every word, you flip the word backwards, and that defines a language reverse of L. Okay, so these are actually quite easy proofs. And the consequence of this is that, aha, this is why the Brozovsky algorithm works. Because in the first step, you take something, this construction that he called flipping the arrows and determinizing is actually turns out to be just applying a systematic functor called the power set functor in a natural way. And looks much less weird and black magic-y than just reversing the arrows. So it tells you, if you've got a reachable thing and you apply this operation, it's guaranteed to be observable. Okay. So now you do it again, you throw away the reachable parts, you're guaranteed to preserve observability and reachability. And now the first step produced something that recognized reverse L. Do it again, you get reverse reverse L, which is of course L. So now you've got a reachable, observable automaton recognizing L. It has to be minimal because every state is reachable and no two states are redundant. So because this thing is stated in this language of arrows, this minimization can be done for automata with vector space structure. So these are a very important class of automata. They're called weighted automata. Topological structure. Convex structure, which is an abstract notion of the notion of convex set. Lattice structure. So various kinds of structured situations can all be done in this Brozovsky style. And this huge step of determinizing, which is causing exponential blow up in set, in other categories, it's just transposing. So for weighted automata, this is actually the best algorithm. So even though it looks inefficient in the example of automata defined on sets, it's actually one of the best algorithms for automata defined on vector spaces. Okay, so I think I will stop there. This was meant to be only a flavor, and it's not something I'm going to examine you in. So if you're not interested, you don't have to read it. But if you are interested, you can read it and talk to me or Rosie, who probably understands this as well as I do. Okay, that's it for today. I will stay for a few minutes in case anybody wants to make any remarks or ask questions. Somebody asked me by email whether she could write, whether she could draw the DFA required for the assignment by hand and scan it. So yes, you can do that, but don't write the solutions by hand. I want to see those things in LaTeX. If you're a LaTeX wizard, there are packages for drawing automata in LaTeX inside Tixi. Okay, there we are. Let me see if there's anything exciting happening in the chat. So Asa wants to know, where exactly are we using set? Well, these are all sets and morphisms, so sets and functions. So it could be that X is a topological space instead.
I asked that right before you answered it.
Sorry?
I asked that right before you answered it.
Oh, okay, very good. Anybody else asking anything? A lot of me neither. I can't see what Dr. Panangarden writes. Is that when the sharing stopped?
Yes.
Okay, good. So, yes. Shouldn't we also remove terminal non-accept states? What does that mean, Maria?
Oh, that was when you were explaining the steps of Brosos. I cannot pronounce that.
Neither can I.
And the Bro algorithm. How do we know that we won't end up with like a state where the only transition is like going back to the same state, but that state is not itself an accept state?
Why should you remove it? Maybe it's meant to be rejecting.
Yeah, I guess. I thought that we should remove it because then if a word ends up there, then it's definitely not in the language. So
Yeah, that's probably what you want, maybe what you want to say.
okay. Yeah, makes sense.
So next time you can't see something, I see this went on for several minutes before somebody bothered to tell me. Please tell me right away. I don't know why the screen froze like that. It just seems bizarre. So good. Any other questions?
I didn't understand what you did at the end with that the power set thing.
That's because you were not meant to. I didn't explain it, did I? So I said there is a thing you can do called the power. You can apply a functor called the power set functor, and it kind of automatically does the steps that Brozovsky described, which is to reverse everything and automatically determinize.
You wrote 2 to the I. I is the initial state arrow, right? So wouldn't you end up with a isn't 2 to the I an arrow from 2 to the 1 to 2 to the X? Is that a
No?
No? Okay.
Two to the I. So these things are. So in the paper, it's every step is spelled out, but 2 to the I is a map that goes from 2 to the X to 2, where by 2 I mean, of course, 2 to the 1. So it's just that same functor applied to the map I. Do you know what a functor is?
Yeah, more
Right.
or less.
So the functor in question, maybe I should share again. Share. Share. Is it moving on your screen? So supposing I'm in the category set, and I've got two sets and a map F like this from X to Y, then the functor is contravariant, and it goes from 2 to the Y to 2 to the X, and we'll call this map 2 to the F. So 2 to the F applied to a subset P of Y is going to basically produce F inverse P, which is of course a subset of X. So if I had this map from 1 to X, right, applying the power set functor to this will give me a map from 2 to the X to 2 to the 1, which I'm just calling 2. Yeah. So this is basically saying the set of final states is actually the initial state of the old machine.
Okay, so applying this functor to the automaton is exactly that.
That's all of Brzezinski, except for the
inverse plus
yes. It's got the
simplification.
inverse built into it. So instead of this, yeah. So it's just a more principled explanation. So I had a completely, so this version of the theory is mainly due to this woman, Alexandra Silva. But she had some sidekicks. And then there was a completely different version based on really exploiting Stone and Gelfand duality, and that was basically due to me and a guy called Nick Bezan Ishvili and Clemens Kupka. So what had happened was I had actually a kind of version which I would say in terms of the modern categorical treatment was half-baked, but that was the thing I did originally with my AI colleagues, and that was all stated in terms of modal logic. So that version, when I started giving talks about it, these two guys, this guy's an algebraist and Clemens is a co-algebraist. So the two of them got together and worked with me, and we put it in a categorical framework. Meanwhile, Alexandra and her gang came up with this reachability, observability kind of duality. And then we realized there was a close connection, and we combined everything, including making a correspondence between the duality here and the duality there. So the duality that we exploited here is a very different nature. And let me see if I can sketch the idea. It's something like this. So we exploited, so first of all, we exploited the following fact. If you have a duality between two categories, which is a pair of contravariant functors that gives you an adjoint equivalence, then you can lift this to a duality between the automata defined on C and algebras defined on D. So this is kind of a lifting of a duality. So once you have this situation, then you can say, let's say I have a machine. I can go to this world and construct an algebra by this appropriate functor. Now the algebras there turn out to have a very special property. There's a unique minimal algebra that's included in A, such that if you take any other algebra that's included in A, then this A0 has to be included in this one as well. So to repeat, the algebras that you get have the following property. There exists a special subalgebra called A0 with the property that if you take any other algebra injected into A, A0 must also inject into A prime. So now what you do is you say, I use the duality, I go there, I look, instead of coming back, because that will just give me the same machine, I come back with A0. So I get a machine M0. Because this is a duality, it flips injections and makes them surjections. And now I'd like to argue that this guy is actually the minimal automaton. So why is it minimal? You give me any other machine and you say, hey, I've got a surjection from M to M prime. So M is collapsed to M prime. I'll say, well, whatever you've done, I can do better and get you to M0. And how do I prove that? Well, I use my duality to come there, and then I exploit the special property of A0. So now I know there's got to be an injection like this, and coming back tells you I've got to have a surjection in the opposite direction. So dualities reverse arrows, and they convert injections into surjections and vice versa. So now I've said this M0 has a property that if you've collapsed M to any M prime, it can always be further collapsed to M0. That was our kind of perspective on minimization. It's very different from this observability duality thing, observability, reachability duality. But now there's a joint paper with like 7 authors in which we've kind of got a super framework that encompasses both these things. So I described this paper as Alexandra mainly and her sidekicks. They're not all sidekicks. Some of them were also heavily involved. Hella Hansen, and I was definitely one of the sidekicks, because basically I had been saying this stuff years ago and people said, no, 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 this is all well known. In particular, Alexandra's advisor told me that. And then Alexandra discovered this thing and showed it to him and he said, oh, great stuff. And she published it. And then he remembered, wait, Prakash told me this like 5 years ago. So then she contacted me and put me on the journal paper. But I would say everything that I presented here is like, especially in this beautiful clean form in which it's written up in the paper, is due to her. Okay.
So can I ask a quick question?
Yeah.
Which modality are you using? Is it the box modality?
You mean when I was describing this in modal logic form?
Yeah.
Yeah, it was kind of a, so what I did was the following kind of thing. So I said, supposing you've got an automaton. So what is it called? States, start state, transition. And by the way, I had a more general notion of an automaton than the usual one. So it had something called obs. It had states, it had an input alphabet, it had an initial state, it had delta, it had a set of things called obs, and it had a map gamma from states to obs. Now the automata that you're used to also have a map from state to obs. It's basically except, not except. but I was considering more general observations. So maybe with every state, you have some lights that come on, and when you hit that state, 3 or 4 different lights come on, and you say, ah, I see, it's green, red, blue. So instead of just saying yes, no, it has a richer set of observations. So it is for these things that I was describing minimization. And so now the modal logic looks like this. Any omega in obs is a modal formula. If A is in A and phi is a formula, then A dot phi is a formula. Now I could have called this diamond A phi. And then what I realized was that there's an equivalence relation on formulas, and you can quotient the formulas by this equivalence relation, and then you can construct a machine from it. And this machine was similar to Alexandra's construction. And then I realized if you do the double dual using the same kind of logical approach, you would get the minimal machine. So this was mainly done by me and a student called Chris Hunt, who was actually a summer undergrad working with me that year. And so then there was a paper with Chris and me and Joel and Doina and another undergrad who did some of the examples called Monica Dinkulescu. But our version was purely couched in terms of logic and not in terms of category theory. And in fact, to appeal to the AI community, we took out the logic and said, these are not formulas, these are experiments. So we didn't use the word logic in that paper. But later on, we really understood that the way to think about this construction was, so this is when I was so excited. I said, I have a new automata minimization algorithm. And I described this to Denis Terrien in the corridor, and he said, let me show you these papers from 1962 by my advisor, Brozovsky. I went, oh, damn. Anyway, there you are. I think I'm supposed to have a meeting with Alika in 14 minutes, so I better eat lunch.
Thanks for the explanation. Have a great afternoon.
Thank you, thank you. So I really need to go because I have 14 minutes to eat lunch.
Thank you, Prakash.
Thank you, Professor.
I hope you had fun.
Thanks, Prakash.
Thank you.
Was Alika there?
Doesn't seem like it.
Okay, I'll